Thank you. Before I start, I would like to thank the organizing team. You guys are amazing. I'm having a wonderful time in Japan, so thank you. So let's start. So I want to talk about data processing and how we do it at Spotify, and more particularly, I want to talk about a library that we created that's called Scio. A bit about me before I start. My name is Julien. GTO is my GitHub handle. I am a data engineer. I've been working in Scala for roughly 10 years now. And I've been working for Spotify for about 1.5 years in Stockholm, Sweden. I work in a team, or squad, as we call them at Spotify, called FlatMap. And, well, I guess the name suggests that we're doing a lot of Scala. And I'm part of units called data infrastructure. So we do all the groundwork for doing data processing at Spotify and machine learning. All right, so who doesn't know what Spotify is? No one. Great. Who is not a user of Spotify? Boo. All right, so Spotify is an audio processing service. So we're doing music and podcast. We have roughly 100 million subscribers all over the world. So that's people who are actually paying to use Spotify. We have about 217 million monthly active users, last time I checked. So that's people who use Spotify at least once in 30 days. You can listen on Spotify about 50 million songs. People created 3 billion playlists, and we are available in 79 markets. So that's just to give you an idea of how big data is at Spotify. So let's get started. Data processing. We have different use cases for data processing of Spotify, obviously a lot. The most obvious one would be we need to pay artists, so we need to know exactly who's listening to what. But we have like more visible use cases like Discover Weekly, which is a playlist that we generate every week, and it's music that you don't know about, but you probably will like. It's released every Friday, I think. Release Radar, which is the new things that the artists you like just released. Again, published every week. Daily Mixes, it's just a collection of the things you listen to, and it's sorted out by its theme. So for example, if you're into Japanese music, you're probably going to have a playlist that contains exclusively Japanese music. We also have something that I think is my favorite of all of that. It's called Your Years Wrapped, and it's looking back at what you did or how you used Spotify during the last years. And it's looking at the songs that you like, and it's going to generate a playlist of your favorite songs of the year, and also a playlist of the things you should discover because you don't know them yet. That one is, I think, one of the biggest jobs at Spotify because it processes all the data of all our users over a period of 1 year. So I guess you can imagine 200 million people listening to Spotify every month, and each of them over a year probably listens to thousands of songs. So that's big data. And the last one, which probably none of you knows about, is called Fine Insights. And it's something that we give to artists. So is anyone publishing music to Spotify? No one. Okay, so you don't know what it is. And it's basically analytics for artists. So if you're an artist, you publish your music on Spotify, and this will tell you who's listening to your music, when, how, where. Maybe you're popular in Japan now, so you need to come here and do a concert or something. So those are just like a few examples of the things we do with data at Spotify. So that means that we have a huge problem of scalability. And I want to explain what it means, scalability, in that sense. So of course, everyone thinks about the size of your job, like maybe my job processes 10 terabytes of data an hour. That's one way to see scalability. That's indeed one of the issues you have to deal with. But that's not the only one. That's just the most obvious one. The other thing you need to think about is just the number of data sets you're going to produce. So we have a lot of users, we're doing a lot of things with data. That means we have a lot of data sets to work with, and that comes with a number of issues. So that's another issue with scalability, and another thing that I mean when I say scalability. And the last one is scalability in terms of the number of people working with data at Spotify. So every year, Spotify has more users, but also more engineers working for those users. And those engineers are different types of engineers. So maybe they're backend engineer, maybe they're data engineer, maybe they're data scientist. So not everyone knows about data processing in the same way. Some people at Spotify will be experts who work with data processing for 10 years. They wrote code in MapReduce, in Hadoop 10 years ago, and know they're writing in Scala, and they're super confident in what they can do with Scala, and they want to do really crazy, complex stuff. But other people are just fresh out of school, and they just want to write a simple pipeline. They just have to do it. Maybe it's not their specialty. Maybe they're just backend engineer, but they happen to have to write a data pipeline at some point. So we need to address really different use cases for really different people, and a lot of them. Someone's talking to me. So it comes with a number of challenges, like doing data processing. So those are the most obvious one. If you wrote Spark code or Scio code or whatever at some point in your life, you know that you have to do scheduling. So you need to say, my job is a batch job, and it needs to run every hour or every day. That's something you have to deal with. You need to do orchestration. So you need to say, my job depends on some of the job that I wrote or that someone else wrote, and I need the data to be available before I run my job. Also, maybe you need to set up some things before your job runs. Or maybe you need to scale a database cluster somewhere because your job would blow it up. There's the processing part, and you can do batch and streaming. And that's pretty complex too. Your logic might do crazy things, like maybe you want to do crazy math. Maybe you need to join different data sets. Maybe it's hard. You want to test what you're doing. You want to make sure that it's not going to blow up in production. I don't want something to wake me up on Saturday at 3 in the morning because the job blew up. I don't want that to happen every week. So I'm going to write tests. I need a way to write good tests. I need to solve the issue of storage. Or how am I going to store my data? Do I have to choose a binary format? I am writing JSON? Maybe not. Maybe not. Good idea. Maybe I need to choose a binary format. Maybe I want to store in BigQuery or in another database. I need to make a choice. And of course, there's the issue of cost, because big data is big money. And there are two sides of things we will think about when you write big data, and it's going to be the cost of running your jobs and the cost of storing the data somewhere. And that's super expensive too. But actually, when your name is Spotify, you have a lot of engineers, you have a lot of data, you have a lot of issues. So you still have the issue of scheduling your data, you're still scheduling your jobs, orchestrating everything. There's also the problem of lineage. So you need to know where the data is coming from, what happened to it, and you need to be able to track this at any point in time. You need to handle permission. You don't want anyone at Spotify to have access to data that's private and sensitive. You still need to solve the processing part. You need to encrypt your data. I'm sure a lot of you guys have heard about the GDPR regulation in Europe that say that you need to do a certain number of things for your users. You need to make sure that the data is safely stored. You need to make sure that only the people who need to have access to the data have access to it, and they have a good reason to have access to it. You need to be able to delete the data of users if they ask you to. That's a huge challenge. Imagine if I have data about someone who's been using Spotify for 5 years, over all the data that Spotify has about everyone for the last 5 years. I need to delete only your things. How do I do that? And you also need to be able to fetch the data of a given user and send it to them if they request it. So that's really, really hard. You also want to monitor your job. So if I have a job running in production, I want to know that everything is going all right. And if something fails, I want an automatic system that tells me, hey, something is not quite right. You should have a look at it before your user notices. I want to make sure the data I'm publishing is of good quality. The worst thing that could happen is not the data not being published, is wrong data being published, because everyone who's using that data will have wrong numbers, wrong results. That could mean a lot of money lost. You need to test. You need to handle latency. If I'm publishing my data, how long can people wait for my data being published? What if something wrong happens? Is it okay to be 2 hours late, 7 hours late, a day late? Maybe not. But you need to think about this. What happened when an incident happened? If I'm using Google Cloud and Google has an issue, maybe my job won't run. What do I do then? You still need to handle storage. You need discovery. A lot of people are using data with Spotify. There's a lot of data available. Huge challenge. How do people find data? I need to write a job. I want to know if the dataset is already available or not. I probably need some data from somewhere. How do I find it? How do I make sure it's good quality? You need to know the life cycle of your data. So again, just need to know what's happening. You need to make sure that the data you're publishing is published automatically. So that means that if I'm generating several data sets, I don't want to publish half of them and not the other half. That would be terrible. And there's other sides of the cost that maybe you're not thinking about. So of course, runtime, storage, but the cost of incidents. If I can't deliver the data, how much is it costing to Spotify? Am I losing users? The cost of lateness. If my data is coming late, again, maybe that has an impact on my users. Maybe they won't be really happy about this. The cost of skewness. If the data is not properly shared, then maybe it's going to break things, and maybe that's going to make my job more expensive than it should be. And of course, there's the cost of productivity. We have a lot of engineers. We don't want them to lose time for nothing. So, I mean, that's more challenging than what you might think about. And of course, at Spotify, those challenges are not solved by a single system. It's going to be a number of products, right? A number of things that just work together to deliver and try to do all those things. So I guess the bottom line of what I'm trying to say here is like, data processing and big data processing is massively expensive and massively hard. If you think about what you're doing when you have a small-ish app, you just maybe install Postgres, dump your data in there, and it does most of the things for you. It does security, maybe encryption, you can query it, you don't need scaling, you don't really need orchestration, everything just works. But when you're doing big data, nothing just works. You have to think about everything. Right, so where are we as an industry and as a company, Spotify? How are we? So I think the point where we are at is that we know how to do data processing. It works. We know how to do it in a reliable way. So we don't have too many incidents, and when they happen, usually we can figure out something, rerun the jobs, maybe backfill the data. We know how to deal with it. And I think that's industry at large sort of knows how to do this. But there are still two things where we are not really good. We're getting there, but we're not there quite yet. The first one is efficiency. How do you make sure that you're not wasting resources? You need a lot of computer to do data processing. That means that it's going to be expensive. That means that you need to have access to this computer somehow. And of course, it has also an ecological impact. You're going to burn a lot of energy. That's not necessarily good. At Spotify, we try to be a green company. So you want things to be fast and efficient and not wasteful. I think we're getting there, but there's still a lot to do. And the last one, I think when we get there, we're matured as an industry. We want things to be easy. So again, if you think about a SQL database like Postgres or any other, you just install it and it works. And then you have a simple language to use it. And you can query it and it's going to optimize things for you. And you don't need to be an expert in anything, even someone who has very limited knowledge. Even when we were studying at university, we could write SQL queries and it just worked. That's easy. And definitely when it comes to data processing, we're not there. Right, so I want to talk about some of the things we're doing at Spotify, and more particularly in Scio, so one of the specific solutions we're developing, to address these issues. So a quick word about Scio. So Scio is a Scala library for data processing, so it does the runtime part. On the right side, you can see a bit of code, like the typical word count. If you've done some Spark, it should look familiar. But yeah, that's pretty simple API. It's based on a product called Apache Beam, which is developed by Google, which is a data processing framework in Java that can be run on different runtimes. So if you use Scio, you can deploy your jobs on Dataflow, which is a Google hosted solution, but also you could use Spark or Flink or any other data processing framework. So you can port it. And it's open source. I do encourage you to go on GitHub and check everything that Spotify is doing. We actually publish a lot of projects on GitHub, and not only about data processing, but we also have scheduling and other things. So yeah, do go on GitHub and check out what we're doing. Almost everything my team is doing is open source. Right, so what are the goals of Scio in the context of Spotify? What is it we want to achieve by writing another project on top of Apache Beam? So we want good documentation. We have a lot of users with different knowledges, and we want everyone to be able to use Scio, and we don't want them to have to look at the code to figure out what's going on. So we need really good documentation. We need the code you're writing your app to be predictable, so you will just know what's going to happen when you write the code, and it just runs. If it works once, 2 times, 3 times, then it should work all the times. We want it to be productive. We don't want to waste the time of our engineers at Spotify. We want people to deliver features, things that will make our users excited about using the app, not writing mundane code that would be just a waste of resources. And because of all those points, we want type safety. I think if you're serious about the 4 points I just made, the only logical conclusion is I want something that is type safe, because type safety serves documentation, predictability, performance, and productivity. So the Scala language helps us with the 2 last points, which is why we're writing this in Scala. Right, so a bit about what we do with Scala at Spotify. We use Scala as the default solution for data processing. So if you're a data engineer at Spotify, you join Spotify, you want to write a job, probably you will be using Scala. You don't have to, but that would be like the default solution. We want to be involved in the Scala community, so we're sponsoring the Scala Center, and we have a seat at the board as a board member at the Scala Center. And we want to do a lot of open source. We want to give back to the community. We get a lot of benefits from Scala, so we kind of want to give back all the things we get by publishing our projects and allowing people to use them. Right, so who is using Scio at Spotify? We have about, so it's kind of hard to know the exact number because people just don't call us and ask, hey, can I use Scio? They just use it. But our estimate would be roughly 350 people use Scala at Spotify. A bit more than that, probably. There are data engineers, of course, data scientists also, and backend engineers occasionally write some jobs. We have thousands of unique jobs, so I'm not talking about running jobs there. I'm literally talking about thousands of applications written using Scio. And we're doing batch and streaming jobs, mostly batch, but we also have pretty big streaming jobs. Right, so in the next part of the talk, I'm going to try to show you some of the things we're trying to do to address all the problems we say we should fix. So efficiency and ease of use. First thing we did a few months ago about serialization, we wanted to make sure that serialization was efficient. So a few months ago in January, we released this new big version of Scio called Scio 070. And the biggest change we had was that we introduced a new way to write static coders. So coders are the things that you use when you want to serialize data. And of course, in the data processing frameworks, that's all the time. So think about it. You have different machines running a program. You need to move the data between the machines. You need to serialize and deserialize data all the time. And we made all the changes, but basically we replaced and we changed the way we were serializing data in Scio. So we used to use a library, a Java library called Cryo, and Cryo does some magic at runtime to serialize data. So it's using reflection. It will introspect your classes at runtime, try to find out what it has to do, and serialize data using those info. And we decided that that wasn't good enough, and we want something that is more type safe. So we want things to happen at compile time and not at runtime. There are several reasons for doing that. Predictability is one. We want to make it more obvious how this is working. We want it to be easier to test, because when all things are happening at runtime, that means that you need some context to make sure that it does the same thing as it does in production. We need it to be fast. We needed granularity, and by that I mean that you have a fine control on how serialization works. But we didn't want the user to have to spend time writing serialization logic. So we want things to be automatically derived at compile time. And in case we couldn't do that, because, for example, if you're using a Java class, you might not have enough information at compile time to derive the coder logic, then we would fall back to Cryo, so that in most cases you don't really have to care about it. Right, so this is what we changed in Scio's code. I'm only showing one function, but of course it was every function in Scio that changed. So basically we used to have the left side in older version of Scio, where anytime you were calling code that might need to serialize data, we would use something called a class tag, which is like runtime information about your class, and then we would call Cryo, and Cryo would do runtime black magic. So it would figure out something. And now what we do is we just say, you need a coder at compile time. You need to know how to serialize things at compile time. So instead of doing runtime black magic, we're now doing compile time black magic, because that's going to be derived automatically. Right. Now, of course, that's a breaking change. So what we did is we also created ScalaFix rules so that you can migrate your code by mostly just applying a script on it, and you will do a lot of the job, and you would just have to fix a few things. Again, we have thousands of pipelines Spotify. We can't just spend 2 weeks to migrate each of them. Right, what happened next? So it's been 6 months now. So I did a talk about serialization already a few months ago, and now I actually have numbers to show how much faster are my jobs. So we have this massive job that encrypts personal data. So anytime you do something on Spotify, we are collecting like events about what you're doing, and those events, maybe they contain personal information. Maybe they contain your name or your address or something like that. And we want that to be encrypted. So that job needs to take your events, take key chains, so the keys that you're going to use to encrypt your data, join the two together, and then use that to encrypt data. That sounds fairly easy, but we have a lot of users, so things, terabytes of data every hour to process. So as you can imagine, this job is both very generic, it works for every event of Spotify, but also very big. When we migrated it to Scio 07, it gave us more control on the serialization logic. And we realized that we're using this thing called generic record, which is like a very generic way to represent data in Java and serialize it. And we realized that serializing that with Cryo was super inefficient. Because we are migrating to Scio 07, we had a lot more control on what was going on. And one of those difficulties in that code was that the schema of the input data and the schema of the output data are not the same, because you changed the data in between. And so if you're using Cryo, it's really, really hard to customize what's happening at each step. But since now everything is compile time, using Scala implicit, we can do some tricks. And with like 5 lines of code, we can have a specific coder for the input data and a specific coder for the output data. So we did just that. And we also made a change in Scio that will tell you if you're using generic record, careful with serialization, not very efficient. Maybe you need to have a look at it. And this is what happened. So that's like one of the biggest events in Spotify, probably the biggest. It's massive. I can't tell you how big it is, but massive. And we did that change, deployed it, and the cost of running that job for that type of event went down 60%. A lot of money. Obviously, I can't tell you exactly how much it saved, but think a lot. The runtime of the job went down significantly. So that makes the life of people who are maintaining that job and do on-call a lot easier because, well, first of all, they know that this job is going to run fine in 1 year. And second of all, if something wrong happens, they can rerun the job, and the data is still going to be delivered on time. So that's pretty good. So I guess the takeaway from this is if you're doing data processing and big data processing, do not overlook serialization. This is going to cost you a lot of money if you do. Think about what you're doing. Maybe it's not really important for you. If you're not shuffling a lot of data, maybe that's okay if serialization is not super efficient. But if you have a really big job that is shuffling a lot of data, be sure that serialization is efficient because maybe a lot of the time and the money spent on that job is just spent serializing data. Second point, we wanted to make joins more efficient. Join is like something you do all the time. And I think when you're joining two data sets, like if one is large and the other is small, so by small I mean it fits in memory on a single machine, super easy, no problem at all, I can do that. If one of the events is really large and the other is like big but not that big, by that I mean it can fit in the disk of a single machine, then a bit harder, but you can manage, it's all right. If the two data sets are large, like none of them fits on a single machine, then it's really hard and really expensive. So we came up with this thing called sort merge bucket join, which is like a different type of join that's pretty old, pretty well known, but it's not implemented in Dataflow or in Beam. And so basically what it does is like it will take your data and sort of shard it in different buckets. So you will say, I want my data to be in 5 buckets, and it will just split the data in 5 buckets for using a key in your data. And in each bucket, the data is sorted. So it looks like this, roughly. So on the left side, you can see my data set. It has IDs. I'm going to share the data by ID. So I'm going to apply a hash function on it, and the hash function is going to give you a bucket number. So in this example, I can see that the IDs 0, 3, and 6 went to the first bucket. 1, 4, and 7 went to the second bucket. And 2, 5, and 8 went to the third bucket. So I choose to use 3 buckets. In each bucket, the data is sorted. So if we have a look at the first bucket, the ID 0 is first, then 3, and then 6. Once I've done that on the 2 data sets, the left side and the right side, I can very easily merge the data and join them, because all I have to do is to take bucket 1 on the left side, take bucket 1 on the right side, and just walk through them, and the data is sorted. So I can just join very easily and very efficiently. And then I do the same thing on bucket 2, bucket 3, and so on and so on. So the benefit of doing that is that you only need to shuffle your data once. And once you've done that, you store it bucketed on disk. And then anyone who needs to join by key, by the same key, can still benefit the data being bucketed. So they can just literally just join, and they don't need to shuffle again. So your joins are going to be just as slow as before, or maybe a bit faster the first time, but then when you do it again for different pipelines or different jobs, it's going to be super fast. So the cost gets amortized over time. We made a PR in Beam. It's going to handle all the tricky bits for you. And side bonus of this, storage becomes more efficient, because what you're doing is like you're grouping data that is pretty similar, because, for example, you'll be sharding by user ID. So all the data for a given user is all stored in the same place, then compression becomes more efficient. So the size of the stored data on disk is much smaller. It can be up to 5 times smaller. And again, saving money. And the last one I want to show you is how easy it is to use Scio. Know that we support a new thing called BeamSQL. And so that's going to come in the next release of Scio, Scio 0.8. And it's about, it's about just writing SQL instead of Scala code for your pipelines. And it's based on something called schema coder. So it's a new type of coder. So basically, when we were working on Scio 0.8 and we made coder more efficient, we were also thinking about Scio 0.7, sorry. When we were working on 0.7, we were also thinking about what we were doing in 0.8 because you need a specific type of coders to support this feature. And it does a bunch of nice things for you. So basically, you can do this. I have a distributed collection, an S collection of users. I want to apply something on it, and I can just write SQL code and say select username and emails from that S collection. And you can see that it's doing a string interpolation, and it will just use that. And then I can say, I want to read this as a pair of string and a list of strings. Right, pretty easy. The problem is, now we're losing type safety. We're writing string-oriented code. So we're using Scala because we want the safety of it. So it's kind of sad that we're losing this to make Scala easier to use, to make Scio easier to use. And so there are a number of things that could go wrong. Maybe I made a typo in my query. It's not even valid SQL. Maybe username and email are not valid fields in user. Maybe the types are not what I expect it to be. And maybe I can't convert those types to what I want to have in the end. So for example, here I expected to have an S collection of string and list of string back. Maybe that's not what it's giving me. Can we fix this? Yes. So we also introduced this feature called typed SQL. So basically, what it is a way for the Scala compiler to understand your SQL code. So if you write that, you just replace SQL by tsql. Then what happens is it will detect at compile time the problem you had in your code. Can anyone see what's wrong in there? If you don't want to speak English, just shout the word that's wrong. Yes, fun. That's not valid SQL. If you do that, the Scala compiler will tell you, well, you wrote this, SQL username, select username and emails from P collection, but from is not the thing. I was expecting order offset fetch from something. But again, compile time, you don't even have to run your pipeline to see that. Maybe you made a mistake in the name of the field. So here I'm saying, give me the name and the emails, but name is not something that exists in my user class. So again, the compiler will tell me, I can't find name, and it will tell me the thing that it can find. So it tells me, well, I can see username, which is a string, and emails, which is a list of string. And then it tells me what I'm expecting to see as a result. So it's telling me you're expecting a string and an array of string. All right, what's wrong with this one? Yes, see, that's a very trivial mistake that you can make. And it took a few seconds to a lot of people to see it. So indeed, I say username, I want to select username, and I want a string, and I want an int, but username is a string, so that can't possibly work. And again, the compiler is going to tell me, well, username is a string, and you expect an int, not going to work. Sorry, need to fix that. Last thing that we can do is Scio is now able to just convert types automatically for you. Because it knows about the schema of your data, because it's using schema coders, if you have a type A and a type B, and B is, for example, a subset of the things that are in A, then you can ask Scio to just do the conversion for you. Like, please just make it happen. And again, it can do it in a type-safe way. So it can convert between Scala classes, of course. It supports Java beans. So if you have a Java class that comes from somewhere and you want to convert it to a Scala case class, it knows how to do that automatically. It can convert between case classes. And it even supports Avro specific records. So if you read data using Java Avro, you can just map that to a nice case class that you're going to work with. And again, if something's wrong, it's just going to tell you. So for example, I have two types, A and B, and A is not compatible with B. So the compiler will tell me, this is what A looks like, and this is what B looks like, and there's a problem. I cannot do it, so please fix it. And that's what I have. Thanks for listening. Do you guys have any questions?
Hi. Thanks for the talk. It was really good. So what execution engine are you using at?
Spotify with Dataflow, so the hosted Google solution.
Okay. So actually, I have a second question. So currently in my company, we're using Flink. Do you know? Can I just use Scio like this, or do I need to convince the platform people to actually implement? Do they need to do something, basically?
No, the only thing that's going to change is, compared to Dataflow, is the way you package your app, because Flink expects a fat jar, and Dataflow just, it works differently, just publish it for you. So, so that's going to change, and you're going to have to be careful with conflicts between libraries and the fat jar, but that's about it.
Okay, so I can basically do that on my own without requiring platforms.
Yes, you could.
Cool, thanks.
Yeah, I had a question about Beam SQL. When you check for the column names, yeah, here, column names and types, how do you know the schema? How does it know the schema?
Ooh, that's a good question. So Beam has support for schemas, but Beam is a Java library, so everything is happening runtime, which in our case is not good enough. We really want type safety. So basically, what we can do is we can derive the schema of your class or your case class using Magnolia when it's a Scala case class, and we can materialize the schema at compile time. If you're using Avro or Java class, we can use some internal logic in Beam to generate the schema for you too, and again we can do that compile time. So we have some macros. They are fairly simple, but some macros, but basically just materializes your implicits at compile time.
So here in this line, is there some implicit or something where it's getting the schema?
Yes, there's an implicit schema for user, like the class that is the input of this. And there's also an implicit schema that's generated for the output type. So here it's like a pair of int and use of string.
Thank you.
Last one question.
We still have 2 minutes.
Sometimes you present word productivity, right? Predictivity, right?
Yes.
What it mean in data
productivity
processing?
Yeah, we want to make it easy for engineers to write code and to be able to focus on the features they're trying to deliver and not like mundane things like serialization, typically. So that's what it means.
Thanks.
ありがとうございました。
Thank you.
それでは時間になりましたので、本セッション終わりたいと思います。最後にジュリアン・トゥルネさんに大きな拍手をお願いいたします。